All right, here we go. Magnetism calculations. This stuff is not that bad. All right, number one. A proton sailing along inside a cyclontron. Okay, there we go. That was weird. At 2.99 times 10 to the 7 meters per second. So, remember, meters per second equals velocity, right? Experiences a perpendicular magnetic field at 3.8 teslas. What is the magnitude of the force that it will experience? So, again, with all these, before you get freaked out and ask questions when you don't need to yet, we write down what we got. Number one, I see velocity, right? So, velocity equals 2.99 times 10 to the 7. If they have that error in your unit, it should be times 10 to the 7. I see magnetic field, right? That's B. Equals 3.8 teslas. Awesome. I know we're trying to find force, so I'm going to leave a space and put force equals. And lastly, I see proton. And we know the charge of a proton. We can look back. I got another sheet for looking. I look back a few pages, so if you see this, blah, 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 blah. Remember, the charge of a proton or an electron is 1.6 times 10 to the minus 19. Right here, right? So our charge, which is Q, 1.6 times 10 to the minus 19. Now, we just got to figure out what formula we're using, right? So we got velocity, field, charge, and force. Well, I went back a page. Velocity, field, charge, force. Bam. So next I'm going to write down my formula. B equals force over charge times velocity. Easy money. Flipping back. There we go. So now plug it in. I mean, this is just like every other problem you've done in physics. So we got 3.8 equals force, we don't have, over 1.6 times 10 to the minus 19. That's our velocity, I believe. No, that's our charge. Times velocity, which is 2.99 times 10 to the 7. And that's it. So what you're going to do for this one is you are going to do this times this, and we'll call that number. I'm not going to do it out. And once you do this times this, multiply this whole side by that. Bam. They cancel out. Bam. So you have this times this, multiply it over, multiply it by this field, and then you're going to have your force, and you should get, pause it, spoiler alert, 1.8 times 10 to the minus 11. And it's a force, so what's our units? It's a force. Newtons. Very good. So, next one, exact same setup. So, again, Tesla's is our field strength, so that's B, 0.6. Meters per second is our velocity, 2.5 times 10 to the 7. We don't have force, and it looks like it's an electron, so same charge. Q equals 1.6 times 10 to the minus 19. So I'm going to set it up. 0.6 equals, force is on top, over 1.6 times 10 to the minus 19 times 2.5 times 10 to the 7. That's our velocity. Do the same thing, multiply the bottom together, and then multiply the whole right side by whatever you got on the bottom to move it over, and then multiply that by your B, this times whatever you got, equals your force. You should get equals 2.4 times 10 to the, minus 12. It's a force, so what's our units? We always have to have units. Newtons. Number 3. A proton moves right at this, What is the magnitude and the direction of the force? Well, okay. So same formula. I'm gonna work this one out much less. E equals this over Q times this. Actually, these first, it looks like every single one of these, you're just finding the force. So the setup is the same. Q times V, multiply that over, so multiply that by B, and then you're going to have force. So essentially every one of these you're doing force equals B times Q times V. I mean, that's pretty much it. I would set it up like this and then move it around, but other than that, like, I mean, you're essentially doing this every time. This times this, multiply that over, and then, yeah. So, this is the thing to note on this one. This says the proton moves at right angles directly out of the page. Moves at right angles directly out of the page. So it's coming towards us. So right-hand rule means it's going to be going counterclockwise, right? The force, or that's actually the field. But yeah, so yeah, magnitude in the direction of the force. Yeah, so it should be up or to the left is our direction. All right, I'm not going to go over the next one. Let's disregard that. That's what you're going to get on this one. But the setup's the same way. And for your force, of course, working it out's the most important thing. You should work it out, pause it, and then find the answer. But this is what your answer is going to be. That's 14. 10 to the minus 14. 1.92 to 10 to the minus 14. Awesome. All right, let's go over this next page. I mean, that other page was pretty easy, so pretty straightforward. Okay, so number 1, a student holds a bar magnet in each hand. If they're brought close to each other, will the force be attractive or repulsive? And then they give you 2 scenarios. A, if there's 2 north poles getting close to each other. Well, if there's 2 north poles, they're going to be repulsive. Remember? Same charge repulse each other. It means push away. And then B says if there are a north and a south pole. Opposites attract, so that would be attractive. So north-north pushes away. North-south comes together. Right? Number 2. The figure to the right shows the magnets. The North Pole, the topmost disk faces up. Which poles are on the top side of the other magnet? Okay, so all you're doing is labeling the top side poles. So if this top side they told us was north, what does this have to be? This, this, this. Now remember, if the top side of this one's north, that means the bottom side of this one has to be south. But all they want us to label is the top side of each. So remember number 1, what we just did, and use that to figure out each. So the top side of this is north. What's the top side of this? What's the top side of this? Top side, top side. The bottom side, obviously, of this first one is south, right? So use what we figured out in number 1 to fill that one out. Also, I'm making a note that they are not attached to each other. It looks like they're floating above each other. They don't want to attach. So I'm not going to give you that one. If you want me to answer that one, let me know. All right. The figure to the right shows a magnet attracting a nail to it, which in turn attracts many paper clips. Which end of the nail is the North Pole? Well, if this is the south and they're attracting, that means this has to be north because they attract, right? Easy. So, and then they just want you to label the rest. So I'm not going to do that. Which one of these is the permanent magnet? Which one of these is the temporary magnet? You should be able to figure that one out. In other words, which one is, this C is saying which one is always magnetic. D is saying which one's just magnetic because it's touching something that's magnetic, right? All right. A straight, right-hand rule number 4. A straight wire has a positive charge traveling east through it. What is the direction of the magnetic field? Well, right-hand rule is traveling east, right? So the direction would be, what is that? If we do this counterclockwise, right? Yeah, counterclockwise. So it would be something like that, counterclockwise. Five. Cross section of a long thin wire with a positive current in it. There's so many ins, ises, and its. It's very hard. A cross section of a long thin wire with a positive current in it is to the right. The current is shown as coming out of the page towards your face. Which way is the magnetic field going? Right-hand rule. Remember, my thumb is the direction of the current, so that means towards us, right? Which means the field should be going, again, counterclockwise. So something like this. If it was going into the page, my thumb would be going down and it would be clockwise, right? Because these point clockwise. And there's a good right-hand rule, real short video. Another teacher does it, but it's pretty good on Canvas. All right, number 6. What if the cross-section of the wire had a positive current moving into the page? We just answered that, right? And number 7. A student makes a magnet by winding a wire around a large nail as shown in the figure to the right. The magnet is connected to a battery as shown. What two things can make the magnet stronger? Hint, to make something stronger, we usually increase things. What can we increase? Well, one of them you'll get right off the bat usually. Typically, if you get a stronger battery, you can make a stronger magnet, right? So that's number 1. Number 2 is we make more coils. More coils, the stronger the magnet. And that's it, guys. You don't have to do this bottom part. You can if you want to. I think the answer's already there. So if you want to get more practice, I mean, you can and you'll have the answers. But other than that, you're good to go. Let me know if you guys have any questions. Hopefully you get this.